Hi, welcome to video 10.4D, roses and tangent lines to a curve at the pole. This second part is going to be important when we get to area, which is 10.5. So recap so far as the polar graphs we've seen already. We've seen lines. A horizontal line, remember, would be y equals a number. So y is our cosine theta. So if you divide, r sine theta. So y equals a becomes r sine theta equals a, and then you divide by sine theta, which 1 over sine theta is cosecant theta. So obviously in this case, horizontal line is way prettier in rectangular form than in polar form. Over here, what you would be able to do is simply multiply both sides. Realize that this is 1 over sine theta, do a cross product, and then you'd see that r sine theta is y. Vertical line, same idea, is x equals a number a. X is r cosine theta, divide both sides by cosine theta, you get r equals a secant theta. A line through the pole would simply be theta equals a number, and we saw that before, how that'll go through the pole, and how that would actually go right through the pole, either first to third quadrant or second to fourth quadrant. And it makes an angle of theta with the horizontal or the positive polar axis. Circles, easy one. Circle center at the pole with a radius of c. So that's an easy one. Circle with a center on the axis and tangent to the other axis. You have symmetric with respect to the polar axis, will involve cosine. And so remember, this is 2a where the radius is a. So whatever number this 2a is equal to, the radius is actually half of that. It'll be symmetric with respect to the polar axis, and it'll be tangent to the vertical axis. If it's r equals to a sine theta, then because of the sine, it'll be symmetric with respect to the vertical pi over 2 axis. And if a is positive, it'll be tangent to the polar axis and above it, whereas if a is negative, it'll be below. We also saw Lima Signs. The general form is r equals a plus or minus b cos theta, or a equals plus or minus b sine theta. Personally, I think your best bet is to make a table. Remember, you're plugging in thetas, 0 pi over 2 pi, 3 pi over 2. Don't forget to check if the pole is on the graph by replacing r by 0 and trying to solve and see if you get something that is true. As far as does it have a dent or is it convex, because if it is a Lima Sign with a loop, it'll have 5 intercepts. A Lima Sign, cardioid will have 4, and in each case those will involve the pole. But if it doesn't involve the pole, there'll be 4 intercepts, and then it'll be hard to decide whether it's with a dent or convex, and that depends on the ratio of a to b. And if the ratio of a to b, assuming a and b here are both positive, if that ratio was less than 2, it's a dent. If it's greater than or equal to 2, then it's going to be a convex. So with a dent, looks like a lime, a vein, or a kidney. Okay, roses, what we're going to do is we're going to graph these on the TI and then analyze those. So if you want to try these along with me, you can enter that on your calculator and pause it right now, and this is what you would get. So of course, no surprise, because it involves cosine, it's going to be symmetric with respect to the horizontal axis. Now, same thing here, it'll be symmetric with respect to the horizontal axis. Now, here you'll notice we have 3 petals to our rose, whereas here we have 8 petals. If you do the same thing with sine, it's going to be symmetric with the with respect to the vertical axis, the pi over 2 axis. Again, the 3 here is going to create 3 petals, and the 4 will create 8 petals. Now, as far as what the 6 has to do with anything, 6 is actually the length of the petal. So if you kind of thought of this almost as a circle, it would be the diameter of the circle. But I call it the length of the petal, the diameter of the petal, if you wish. Okay. So what do roses look like? R equals a constant times either the sine or the cosine of an integer multiple of theta. If this is not an integer, if it's a fraction, it's a whole different ball game, and you need to use a calculator. So these are going to be roses. The center of the flower will be at the pole. And that's what I'm talking about. A will be the diameter of the petal. If n here, the coefficient of the angle, is odd, that's how many petals there are. If it's even, then it's 2 times that number of petals. Okay? Now, the angles between the diameters of each petal are going to be congruent. So notice here you have 90 degrees, 90 degrees, 90 degrees, 90 degrees. Over here, if you have 5 petals divided by 5, there'll be 72 degrees between each one. However, we're not really going to look at it that way. We're going to look at it as tangent lines to the curve at the pole. So we're looking for, basically, these petals are squished in between these tangent lines to the curve at the pole. These will determine how fat or skinny the petals will be. And it'll also be what we're going to use for area later on. So because it's at the pole, all you have to do is take the equation and replace r by 0 and solve for theta. So let's say you did that and you got theta equals pi over 4, 3 pi over 4, then you would know that these are the tangents to the curve at the pole, and you'd know that your petals lie in between those dotted lines. Okay? When we do get to area later, you're going to see that the area of the whole petal is really 8. Sorry about that. Hi, sorry about that. So later on you'll see that the area of all 4 petals is really 8 times the area of half a petal, and the way we're going to do that, our limits of integration are going to be this tangent at the pole, and we're going to, of course, realize that this petal is separated in half by the horizontal line theta equals 0. Okay, so here's an example. R equals 5 times cosine 3 theta. This will be the diameter of the petal, and because this is odd, we're going to have 3 petals. So in order to find them, it won't take long. You don't have to go all the way down this list. If you replace theta by 0, cosine of 0 is 1 times 5 is 5. So you have a 0.50 right here. By the time you replace theta by pi over 2, 3 pi over 2, you'll get 0. 5 times 0 is 0. That's the pole. If you were to replace theta by pi, the cosine of 3 pi is negative 1, and you get negative 5 pi, which, by the way, is the same point you started out with. You really need just the first endpoint of the first petal, because then you know that you have 3 petals. You could do it by the angles. I'm not going to do it that way. I'm going to do it by the tangents at the pole. So we take our equation, we replace r by 0, and we solve. Divide by 5. If the cosine of an angle is 0, then of course you've got to be either at pi over 2, 3 pi over 2, etc. But your angle is 3 theta. Dividing all of those by 3, you get the following. So here's theta equals pi over 6. Here's theta equals pi over 2. Here's theta equals 5 pi over 6. And then they start to repeat, because theta equals 7 pi over 6 is the same line as theta equal pi over 6. So really, you have these 3 dotted lines. Now, because we have 3 petals and 6 spaces between the dotted lines, we have 1, 2, 3, 4, 5, 6 spaces. Therefore, there must be a petal every other space. And of course, we know the length of the petal. Here's another example. Length of the petal, or diameter of the petal, is 2, and because this is even, there will be 8 petals. If you plug in 0, you'll get 0, so that's the pole, so that doesn't tell you anything. Now, you notice I'm not plugging in pi over 2 because I'll get the pole back again. What I purposely do is, I know I'd like this angle to be pi over 2 because the sine of pi over 2 is 1. So I purposely plug in pi over 8, since 4 times pi over 8 is pi over 2. And that'll give me 1 times 2 is 2, so there's my first petal, and really that's all I need. And I need the tangents at the pole. Replace r by 0, divide by 2. The sine is 0 at 0 pi, 2 pi, 3 pi, etc. But our angle is 4 pi. Divide each of those by 4. You get theta equals 0. Theta equals pi over 4, pi over 2, 3 pi over 4, and then they start to repeat. So we have 8 petals, and we have 8 spaces between those dashed red lines, and so there'll be a petal in each space. Here's another one. Again, diameter 4, number of petals 3. Again, I'll purposely replace theta by pi over 6 so that this becomes pi over 2. Here's my first petal. Here's my tangents at the pole. 3 petals, 6 spaces. There'll be a petal every other space.